Hello guys, today we will be discussing about magnetochemistry. It is apparently very complicated topic due to the derivation of its many complicated equations. So I will try to break it down as simple as possible so that you won't have any problem solving any questions of any university or for any competitive exams like CSIR or GATE. First thing you need to remember that it deals only with systems having unpaired electrons. If their system do not have any unpaired electron, it don't have anything to do with magnetochemistry. Now we can classify all the complexes present in the universe into two sets, kind of paramagnetic and diamagnetic. Paramagnetic compounds are generally attracted towards magnetic field, and diamagnetic compounds get repelled to applied magnetic field. So again, we can classify these paramagnetic compounds in few subsections like ferromagnetic and antiferromagnetic. In paramagnetic, there are some unpaired electrons. This could be like this one. If you draw they may orient like this in any direction. So when any magnetic field applies to the paramagnetic, so they are get some orientation of they are get aligned in the direction of the applied magnetic field. So thus paramagnetic compounds get attracted towards the magnetic field. But in case of diamagnetic compounds, there are no unpaired electrons, so they ultimately get repelled. Now, what is ferromagnetic and antiferromagnetic? Ferromagnetic are by default they have the alignation like this one. So since they are already aligned in one direction, so they get strongly attracted to the the magnetic field. And in case of antiferromagnetic compounds, they have orientation like this one. So in general, they have a kind of orientation of one electron center, and the neighboring electron center kind of cancels the net magnetic moment of the compound. So thus it behaves the opposite of ferromagnetic compounds. Now, as we know that when we increase the temperature, the orientation of any compound changes. The stable orientation gets disturbed, due to which, as the temperature increases, the orientation, the entropy will be increasing, and the orientation will get more random. So that is why it will get difficult to get aligned in same direction. So that is why, as the temperature increases, the magnetic susceptibility decreases. in paramagnetic compounds, right? Same thing happens with ferromagnetic compounds. Ferromagnetic compounds, as by default it has orientation in this way, but as the temperature increases it gets some randomness like this, and so ferromagnetism it get converted to paramagnetic. Whereas in case of antiferromagnetism, we can see that it is by default, it is aligned against each other, but as the temperature increases it gets some randomness, so ultimately the magnetic magnetic property of antiferromagnetic compounds increases with temperature. If we plot the tendency of magnetic property, magnetic nature, the magnetic susceptibility of these compounds against temperature, we may get some plot like this. This is magnetic susceptibility, and if we increase the temperature for paramagnetic compounds, we will get a curve like this. It decreases with the temperature. For ferromagnetic compounds, it decreases first of all steeply, then after certain temperature it the rate of decrease will be lesser. So after certain temperature it basically gets converted to ferromagnetic compounds, and this point we call is as Curie temperature or Curie point. This is for ferromagnetic. And for antiferromagnetic compounds, we will get a curve like this. The increase is due to basically at normal temperature it behaves kind of like a diamagnetic compounds, because the magnetic centers are cancelling each other, but with increase in temperature the magnetic susceptibility increases due to the randomness. Okay, so after certain temperature, this we call as nil temperature. So after this temperature it will get converted to paramagnetic compounds. So at this point is antiferromagnetic, antiferro, it get converted to paramagnetic. So you need to remember these 2 points. This is very important. The nil temperature and Curie temperature. Curie is for ferromagnetic and nil temperature is for antiferromagnetic. Both are getting converted up to paramagnetic compounds after these points. Right. Now let's move to the other points which are basically more important in terms of exam point of view. So the calculation of the magnetic moment, that is we refer it as mu effective. So there are few formulas you need to remember, and if you remember these formulas you will face no difficulty solving any questions from any university, at least for post-graduation and undergraduation courses, or for any competitive exams. So I'm sure that you will not have any difficulties. So you need to remember 3 to 4 formulas. So although the derivations are so much complicated, so you don't need to learn all those, at least for the academic purpose. For higher studies like for research or writing research papers, you need to study further, but at this moment I'll giving you some formulas, and if you remember this you will never have any difficulties. So let's begin. So before that let us understand how the magnetic thing generates. So as we have read in school, the physics courses that any charged thing or any current passing through a loop will create some magnetic moment. So here if we consider the movement of the electron, so it revolves around the nucleus like this. Again, the electron itself revolves around this own axis. So there are two kind of magnetic moment generators. One is for its spin and another is for this orbital movement. So there are two components to the overall magnetic moment. So if we calculate the mu of spin only, so it is you need to remember this formula, n into n plus 2, that's it. N is the number of unpaired electron. So if we have one unpaired electron in the system, it will be 1 plus 2, it will be under root 3, this one. So like this, for a spin only, to calculate the spin only magnetic moment, you need to calculate how many unpaired electrons are there in the system. So for T1 to T9, you can easily calculate by simply putting the number of unpaired electrons. So I will give you some trick when you are in a hurry, so you don't need to calculate all this. You just need to remember, if there is one unpaired electron, the mu of spin will be around 2. For when it is 2, the value is around 3. When it is around 3, the value will be around 4. So if there are multiple choice questions or something like that, so if you are getting the if the value of mu spin only is around any, suppose it is around 4.9, so you have to understand that it's around 5, so there are 4 unpaired electrons. How? Let us calculate. So as you can see that for one electron, the spin only value is, the nearest full number is 2, integer number is 2. So that's why I told you that. And in case of when the electron number is 2, the value will be root over 8. It nears about 3. Similarly for 3 it will be around 15. For 4 it will be around 5, because it will be how much, like under root of 4 into 5, so it will be root over 20, which will be near about 5. So this is one way to save your time. Now let's move to another formula. Now after calculating the spin only, if we need to calculate the mu effective, that is mu total, so most of the compounds of 3D transition series will basically have the value near about the spin only. There will be very little contribution from the orbital moment or no contribution. So we need to remember, when there will be the T2G orbital is unevenly filled. This is the important thing. When the T2G is unevenly filled, then there will be some contribution from the orbital, and the formula will be the total mu effective. We need to calculate it like mu spin only multiplied by 1 minus alpha by lambda by delta. Where this alpha is a constant. It has value of 0 to 4 depending on the ground state term of the metal. Let me tell you how it happens. So for D1 system, if we calculate, if we say the electronic distribution, it will be like this one. So since this is unevenly filled, so there will be some contribution and we need to apply this formula. And here for determining alpha, alpha is 0 when the ground term is S, is 2 when is D, and when it's 4 when the ground term is F. Now you need to understand that for all the transition metals from D1 to D9, there are only two terms possible, that is D and F. So for D1, D4, D6 and D9, the ground term will be D, the alpha value will be 2. For rest, D2, D7, D8, D3 and D3, the term will be F and the alpha value will be 4. So let me show you how. So if you consider the filling of this d orbital, we know the L value is +1, 0, -1, -2. So if there is one electron, so the capital L value will be 2. It is to be 2, and 2 corresponds to D, because we know L value is equal to 0 for S, 1 for P, 2 D, 3 for F, 4 G, etc. So when there is 2 electrons, the L value will be 2 plus 1 will be 3. So the term will be F. So similarly, if we calculate the others, like let us calculate a few more. If we calculate D4, so the net value will be +2 + 1, 0, -1. So the net value will be L is equal to +2. So we will get the term. So you need to remember D1, D4, D6, D9, the term will be D, alpha value will be 2, and for rest the alpha value will be 4. Now let's come to the term alpha. Alpha is a spin orbit coupling constant. It will be a given term. Okay, so and the delta will be the 10 dq for, you know that the difference between the T2G levels and EG levels. If there is this can be calculated through that from the UV spectra due to the transition electron transition takes place from T2G to EG level, so it will also be given the value of this. Now one thing you need to remember is this overall term, this one will be positive in case of when the the D cell is less than half filled. And so let me tell you in this way, this constant, the alpha, will be positive when for D1 to D4, and it will be negative for D6 to D9, right? So when it will be negative, so the overall this value will get positive, so the mu effective will be more than the spin only value for D6 to D9. So if orbital contribution takes place, then for D1 to D4 it will be lesser than the spin only, and for D6 to D9 it will be more than the spin only. So if there are options, like for MCQ questions, the observed mu magnetic moment is greater than the spin only, which you can calculate by calculating how many unpaired electrons are there. So you can predict that whether there is orbital contributions in the system or not. Let's take an example so that to make it simple. So let us take an example of cobalt 2+ system. So it is cobalt is D7 system. So the electron filling will be this 1, 2, 3, 4, 5, 6, 7. So here we can see the T2J levels are unevenly filled, so there will be some contribution towards the overall magnetic moment. For this compound of cobalt, Mag2/6, the value of alpha is given 1030, and this is 12,000. So now if we calculate the mu effective, we first need to calculate the mu of spin only. Then after that we need to calculate this value, 1 minus, let us see, lambda by alpha by delta. Oh, sorry, this one is lambda value, this one is alpha. So to calculate, first of all we need to calculate how many unpaired electrons. We can see there are 3 unpaired electrons. Sorry, so for this compound, actually this is low spin one, right? So the configuration will be 1, 2, 3, 4, 5, 6, 7. So there will be 1 unpaired electron, right? So for 1 unpaired electrons, we know the term will be T. So the alpha value will be 2. So if we could put in this formula, so for 1 electron, the spin will be n into n plus 2, 1 minus 2 into 1, 0, 3, 0 divided by 12,000. So it will be root over 1.73 into, let me calculate it, 2060 by 12,000 So ultimately it will be like 1.87. So you can see that the mu effective is increased from the mu spin only. So as I told you, when there is for D6 to D9 system, the mu effective will be greater than mu of spin only. And for this, I am writing this again just to make you remember that if you remember this one, so you just, for a multiple choice questions, you don't need to calculate. Sometimes, I mean, suppose for this question, suppose the MCQ questions is like that after the orbital contribution, so we are finding kind of what will be the mu effective. So you know that after looking at the unpaired electrons, you can see the mu spin only will be 1.73, and if the options are like 1.87, 1.63, 1.48 or 1.57 like this. So if you remember this line for T6 to T9, if the orbital contribution takes place, then mu effective will be more than spin 1. So you can easily say without calculation that it will be the answer, right? And that too with convincingly. There is one more formula you need to remember. Mu effective is equal to under root of n into n plus 2 plus L into L plus 1. L again you need to calculate as we have calculated previously, like this one. So this formula applies for 4D, 5D, etc. So for 3D, I mean transition metals, this formula doesn't apply. You need to remember just for 3D elements, you need to remember the formula of spin only, that is this one, and this one if there is some orbital contribution takes place. So they might giving you, I mean, confusing options like this. So you need to remember when L in L plus 1 will come, this one will be for, if I mean for not for 3D. Okay, so for 3D, this, I mean, this formula doesn't apply. So you just need to remember these few formulas. I am again writing for spin only, n into n plus 1, and when orbital contribution takes place, it will be mu of spin only minus alpha into lambda by delta. That's all. These three formula, and this one is for 45D, this one is for everyone, and this one is for 3D elements. Okay, so that's all. If you remember these 3-4 formulas and you try to solve any questions from anywhere, I'm sure you will not have any difficulty. Thank you for watching.